All right, well, welcome everyone. I am JJ. Let's tackle an example problem. So we're saying in this one, let's use our area method to draw the shear and moment diagrams for our beam shown. And then we're given our support reactions. AX is 800 to the left, AY is 2,300 pounds going up, and DY is 1,500 going up. If we're using the area method, we're really just coming in and applying all of these rules. If I have a force going up, my shear immediately goes up. If I have a force going down, my shear immediately goes down. And neither of those are going to make an immediate impact in my moment diagram. For an applied couple moment, if I have a counterclockwise one, my moment immediately decreases. If it goes clockwise, my moment immediately increases. And for our distributed loads, we're going to say our shear at the end of a distributed load is going to be the shear at the beginning of that distributed load minus whatever the area of the distributed load is. So we'll make areas for every distributed load. Also for moments, our moment at the end of any shear area is the moment at the beginning of it plus the area of our shear. So we'll area out our shear diagram once we've made it. There's one other new thing in this. If we have this 1,000-pound force is not actually on our beam, to adequately account for that, we're going to have to do a little bit of equivalent loading. So we're going to start there. Equivalent loading. Equivalent loading. Really, we're trying to figure out how could I replace that 1,000-pound force with something that's happening right there at point C. So if we remember our early statics, we said we can move a force to a new line of action and get an equivalent thing if at that new place we still have the same tendency to translate and rotate our object. Really, we said we could just directly take our force and move it to our new location. If we're doing that, let's break this into a y component and an x component. So we're moving this to C. So we'll get a cy and a cx. Our cy, if we're moving that down, we don't change the y component. It's just going to be whatever the y component was originally. 4/5 of 1,000. Or this is 800 pounds going straight down. 800 pounds going down. Our cx would be, again, we're just straight moving it down. We're not changing the force in the x direction. We're preserving that translation or some of the forces from this force. So cx would just be whatever its x component was. 3/5 of 1,000. Or that's going to get us 600 pounds going over to the left in there. Also, my AX, I totally wrote 800. I just grabbed the wrong number. That should be a 600. Let's update that really quick. It's not going to impact our problem, but let's make it right. But from here, I have my CX and my CY. I also need the same tendency to rotate. Right now, that 1,000-pound force will cause a rotation about point C. When I move it to C, if it acts through C, it doesn't anymore. So I'm going to have to stick in a couple moment in that. So I'm going to come in here. The Y component wouldn't cause moment about C, only the X component. So let's do positive, goes clockwise, and we're just getting what's that couple moment that we're going to apply at point C. Our moment about C from just this 1,000-pound force should be, well, again, our Y component causes no moment. Our X component will cause a clockwise rotation. Force times distance should be 3/5 of 1,000. Or that's really just our cx value in here, times that distance we moved it down, 3 feet, times 3. Or I'm going to have to introduce a couple moment in here that's 1,800 pound-feet going clockwise. Or really, in my free body diagram, let's go ahead and add these three things in. I'm moving this force from E, so it's actually being applied onto our beam, and I have to get a CY in here, 800 pounds, going straight down. So going down, I would have now 800. 800. Straight down. Going to the left, I would have, going to the right, I would have my CX. To the right, so we can add that one in. CX is 600 pounds. And our very last one that we have in here is our couple moment. I need to stick a clockwise moment on this right at point C where I relocated that force to. So going clockwise, it is 1,800 pound feet. So now I do have a moment on my beam. Again, we've relocated that so it's actually on the beam. But now I can come through and just apply my rules in here. So I'm going to start out, and we always start at the origin. So we put a dot at the origin and work left to right across this. Immediately I hit AY. So I go from 0 up by AY, straight up 2,300. To keep going with that then, let's go ahead and label this. This is 2,300. But to figure out my next point that I want in here, I'm going to need to know this area. So let's call that, it's the first area we're working with. Let's call this area 1, A1. And A1, we can just come in and say, area 1. The area of a rectangle is base times height. The base of this is 6 feet, 6, and the height is 500 pounds per foot. So 6 times 500 is going to get us, that's 5,000, not 500. 6 times 500 is going to come in and get us 3,000 pounds equals 3,000 pounds. So I'm going to go from 2,300 and we'll decrease the shear at the end of our area is the shear at the beginning minus the area. 2,300 minus 3,000 is going to get us that we'll end up down here at this point right here at negative 700. And we'll label it. We had a constant for our distributed load, so I should see the integral of a constant, a linear function here, as I drop straight down. And then we are constant in that next interval. There's no distributed load, so I can go straight over. Staying at negative 700, I get to the end of my next section. I'm at point C now. That x component doesn't change my internal shear. It would change my normal force, but nothing here to the shear. So I don't need to worry about it. I don't need to do anything with the moment. It will impact my moment diagram, but not the shear diagram. But I need to get in my 800 pounds, going straight down. So we'll drop down. 700 minus 800 is going to get us to negative 1,500. And there's no distributed load here, so we be constant all the way across. At the far edge of this, I get to my roller. I know my dy was 1,500 going up, so we'll immediately jump back up, closing us out at 0. Which finishes out that shear diagram for everything. There's one other thing we do want to do in here, though. I had my shear right here, sloped across the x-axis. So I want to come in and say, that should be a max or a min point in my moment. I'm going to want to figure out my distances to that point in here. So let's come in and we'll call that from the left edge in, we'll call this x1. And from that 0 shear to the end of my linear portion, let's call that x2. And I can use proportional triangles to get those. My x1 over 2,300, my ratio of base to height in my first triangle, is my ratio of base to height in the second, x2 over 700, is my ratio of base to height in an entire triangle in here that goes x1 plus x2, well that's 6 feet, divided by my entire y, 2,300 plus 700, which is our area in here, 3,000. I can solve that. x1 over 2,300 equals 6 over 3,000. x1 is going to get us to 4.6 feet. 4.6 feet. I can also solve to get x2 from that. x2 over 700 is 6 over 3,000. My x2 should be 1.4 feet. Which gives me enough that I can find areas in every other section. So let's come and name them off as well. Our big triangle, let's call that, we already used area 1. So let's call it area 2. A little triangle is area 3, area 4, area 5. So 4 areas for us to come in and find, and we can tackle the rest of our problem. Area 2 should be, well, the area of a triangle is 1/2 base times height. The base of this is x1, so 4.6 times our height, 2,300. Or this area 2 is 5,290 pound-feet. My area 3 is also a triangle, so 1/2 base of area 3 is x2. x2 we just got is 1.4, so base times my height, -700. Or area 3 ends up being -490 pound-feet. And area 4, we're back to a rectangle, or we're using a rectangle. Area 4 is just base times height then. So my base of area 4 is 3 feet. 3. My height is -700. 3 times -700 is -2,100 pound-feet. And finally, area 5. Area 5 should get us, again, a rectangle, base times height. Our base is also 3. 3 times our height, -1,500, is going to get me to -4,500 pound-feet, which would be our last area we need. From here, we can start working across our shear diagram. Again, we always start at 0. We should start and end these at 0. But so we'll get our dot here at the origin at 0. There's no couple moment right here, so we can go straight to our area. We know our moment at the end of an area is the moment at the start plus our shear area. Our moment at the beginning is 0, so 0 plus area 2 plus 5,290 will get us that maximum up here is 5,290. We're increasing up to the very top point here, 5,290. We had a linear function for our shear. If we integrate a linear, we get a quadratic. So we should have a quadratic function, shear slope down, so moment should be concave down. So we should look like that. From there, we can say, well, our moment at the end of area 3 is our moment at the beginning, 5,290, plus area 3, 5,290 minus 490, is going to get us to about 4,800. Not about 4,000. It is 4,800. And that should be about right there. From there, we can keep going with that. Our next point we can plot is, well, what happens after this? We'll go from 4,800, and we'll look at area 4. At the end of area 4, we should be at 4,800, the beginning, plus area 4. 4,800 plus a -2,100 will get us down to 2,700. 2,700. That should be a linear because we were constant for our shear. So straight line over. At that point, we do have a couple moment right here. Don't forget about that one. From our equivalent loading, when we move that force down. If we don't do this, we're not going to actually get the right answer for everything. But clockwise makes our moment increase. So we'll go -2,700 plus 1,800. We're going to jump up immediately to 4,500. At which point we can then go back and say, I'm going to move that 2,700. It's going to be in the way. 2,700. But we can decrease by area 5, or our 4,500 plus a -4,500 gets us back down to 0 to close out our moment diagram, which would be our final answer. Anytime that something isn't applied onto the beam, we're probably going to have to do equivalent loading to move it over to where the beam's actually at. But we can get through that. Hopefully this is a useful video for us. If it was, hit those like and subscribe buttons. Stick around. Let's get you an A with JJ.